We'll continue our discussion on this unsupervised learning. And in the last class, we discussed about k-means clustering algorithm. So we'll see that we can extend this concept of this approach, extend this approach to a further to a more general framework where uh, we can consider the expressing the probability density function, or rather probability densities mm, of the input observation space as a mixture of probability density functions. And just mathematically we can represent it in this form that if I consider x is the corresponding feature vector, then probability of x can be considered as the as the sum of joint probability of x and different density functions, different processes which are represented by the probability density function. So GI here is a density function, and which also represents some kind of underlying process which is responsible for generating feature vectors. So there are contributions from different processes, and each process has its own density function, and there is a probabilistic way these processes are selected. It's a kind of generative model. You can consider with probability PGI, the GI distribution is playing role for the operation, for the generation of the feature vector. So the computation in that case, because you have the corresponding input data set, and there you can always estimate this kind of density functions in the input space itself from the observations. So here also you see that this k is a hyperparameter, which is the number of components, and it is the same hyperparameter in the k-means clustering algorithm, where we are considering number of clusters. So clusters here are equivalent to this components of the mixture density. So this is the PGI is the component proportion. So as I mentioned, the GI defines the ith group or cluster, and k is a hyperparameter. And once again, it should be known as it is required to be known for the k-means clustering algorithm. So we will particularly discuss this approach with respect to a very well-known density function, that is multivariate Gaussian distribution. We are considering multidimensional feature space, so we have to consider this multivariate Gaussian distribution, and we have already discussed about this distribution when we discussed about Bayesian inference using parametric approaches. And you know that in this density function, there are two types of parameters. Two parameters. One is that mean vector or expectation of the density expect mu I, and the other one is the covariance vector of the different fields of random variables. So that is given by the sigma I. So the problem here, problem statement is that if I give you the data set, input data set, like as you say, set of input to data samples, which is represented here by this x superscript t. So if I give you that input data set, so how do you estimate this parameter which best represents the probability density function that could be derived from this data set itself? So so what are the parameters here? You can see that if you have k density functions, k density density function. So for each density function, you have its corresponding expectation mu and corresponding covariance sigma, and then of course we call it prior also sometimes, and with respect to this, it is the probability of having the density functions. So this is the problem, and here we are, so what is the difference uh, from our earlier approach? There we have not assumed any kind of density function. So it's an implicit no, assumption was that, as I mentioned, that shapes would be hyperspherical. So some kind of Gaussian assumption is there, but we assume that mostly so that those centers, they are actually representing these means. But we have not considered any estimation of covariance matrix because no, we considered this covariance matrix is the same for every every clusters, and so when we have used a distance function, we considered the Euclidean distance function. But in this case, there is a distance function called Molinovi's distance function, where you can consider the distance between the feature vectors of different groups. So you can normalize them using this covariance matrix, and that could be useful here also. But we will see actually this algorithm has a different flavor. It is not exactly the same simple way what we do in the k-means clustering case. That of course the flavor is there still. We will consider an approach called expectation maximization approach that I will be discussing here. So these are the things. So we'd like to refine that approach so that now we can take care of estimation of these parameters. Also, the other estimation of the priors of each density function. So, if I consider the estimation of the parametric probability density function, so now we have a new set of parameters. Like here, you can represent this the probability density of a feature vector x using this set of parameters. So for each density component, you have pi k, which is the proportional or the probability of that particular density function, pi k, or proportional amount. I should say that is the probability, like a prior probability of having the process represented by k for generating x. And then its mean mu k, and then the covariance sigma k. So pi k is also, there is a term called mixing coefficients or proportional coefficients. So expectation maximization algorithm that we'll be considering here, like in k-means clustering also, we have started with certain initial partitioning. That is the kind of, we expect that could be a good partition. Then we computed parameters. Then we observe that no, we refine the estimate, and we again go for new set of partitionings. So we try to the expectation stage tries to impose a certain kind of no, I should say intuitive partitioning, intuitive guess on your data sets, and then from there you estimate the parameters. You compute the, or rather no, from there you compute the the corresponding. So if you have all the parameters, so here it is not partition. Here actually you start with an initial set of parameters, and with respect to that, you assign you compute the probabilities of x belonging to each cluster, and then after that, with this redistribution, again you re-estimate those parameters. So if it is a good initial guess, it should have got the same set of parameters, like what we did in k-means clustering. We started with an initial centroid. Here also we are doing it, but we will be refining all these set of parameters in the probabilistic interpretations. So we'll see how we can do it. And there is also, so this is the expectation step that you can see here. So you see that this expectation step, so we started with an initial set of parameters, and there what we are computing the probability of x belonging to the kth Gaussian cluster. So this is Zik. So I have not shown you how the Zik will be there. So this is how the Zik is computed. You can see that Zik is the corresponding density function of the kth group, that and then it is multiplied by the corresponding mixture coefficient, which is acting like a prior, and there is a normalizing, there is a normalizing term which will normalizes this probability sum of all no sum of zik over all k, it should be equal to 1. So that is what you are doing here. You are considering that this is a normalizing term, right? So right. So that is what you will considering. You see that for ith component, so for ith this is a normalizing term. So it assumes the probability, computes the probability of the pixel, or I should say the feature vector ith feature vector to the kth component. That is the probability. And then you may assign x to mth cluster. So that is in k-means clustering. That's what we are doing. But no, it is not required in the sense, because these probabilities are sufficient, which reflects the assignment. So crisp assignment may not be required. We can carry on with these vectors and use them in re-estimating the parameters of this one. So we'll see in the next case. So this step is a bit optional. In fact, when we finally arrive at a good estimate of these parameter sets, then only we can apply this step to get the corresponding clusters. So we have to iterate, still we get a convergence. So this is how this refinement goes through using the ZIK computation. So that is the difference with k-means clusterings. There, this decision was crisp. Only one cluster, contribution to one cluster is considered, that is being counted. But here, the contribution of that feature vector to every cluster in terms of their probabilities are considered while refining this set of parameters. So this is in the computations, if I explain, that would come. So you can see that number of elements in the kth cluster or kth group is actually sum of all these probabilities. So in the k-means clustering, this value was either 1 or 0. So that's why you can count simply what is the number of elements there. But here it is a probabilistic interpretation. It is a probability. So the sum of probabilities will give you this number. So this number is not an integer, right? This number will be a real number, of course. So it is the expected number of, I said pixels, actually it is in terms of images, it is many times it is explained, but no, it is feature vectors you should consider. So again, you can see that the parameter mu k, which is once again, this is the expected value of the average, weighted average of all these feature vectors belonging to that class. And in fact, the weights are belongingness to that class in terms of probability. So this is what is the weighted average. You see that nk is nothing but the sum of these weights. And similarly, you can compute also the covariance matrix using these weights in this fashion. So you are using every feature vector and their probabilities to that particular group, group to refine this estimate. And finally, pi k's are also can be estimated in this way. So that is why I mentioned that no, you do not require this crisp precision of assignment of a particular feature vector to a particular cluster. You can simply compute its joint probability ZIK estimated, use it for refining these parameters, and it continues this expectation and maximization, these two steps, EM steps continues till it get a convergence. So that is what I should say a more general framework. Under more general framework, the k-means clustering can be understood. When these probabilities are either 1 or 0, then it becomes simply the same as k-means clustering. And you are not really computing their covariance matrix also. You assume all the covariance matrices are the same. Now, let me then switch over to another approach, which is whose motivation, whose objective is a bit different than what we discussed earlier. We have considered simple clustering, that is simple partitioning of the input data based on their similarities and trying to identify those groups. But what about the interrelationships about these groups? That is also one of our objectives. And there are clustering algorithms which addresses both the things together. Now, this could be done in two steps also. It could be done that you get those clusters and then try to find out interrelationships and build a hierarchy. But you can have also some algorithms where the clustering itself is developed by building this hierarchy. So you get clusters at different levels of hierarchy. So, so this is called, this type of approach is called hierarchical clustering. As you can see that it builds hierarchy of groups, and it could be top-down or bottom-up approach. But I'll discuss here bottom-up approach because that is more popular. And what is interesting here, in this case, instead of directly using this feature vector, we can all use the distance matrices. So that is one great advantage because you can reduce the dimension. You can see that if you use distance matrix, your feature vector could be of a very high dimensional feature vector, but when you compute a distance between them, then it's a scalar value between a pair of feature vectors. So if there are n feature vectors, you have only n choose 2 values. Earlier it was n feature vector, and for each case you have a d-dimensional. So your space requirement maybe it could be quite small when you consider very high dimensional data. So you can use simple distance matrix without going into the feature vectors. And also it means that if you define these distance matrices, sometimes we have used this concept of kernels. So where you extend this concept of clustering also to non-numeric representation. So where you require to define the distance matrix. So that is also another advantage of this particular representation. So explicit feature representation is not required, as I mentioned. A non-probabilistic approach that we'll be considering. It doesn't mean that there could not be any probabilistic approach. So the hierarchical clustering, I will explain with. Now this is taken from a book by Pavel Pezner in the bioinformatics books, and the slides are also from Pezner's slides. So here the examples are shown here. You can see there are I think there should be 10 samples are there, right? There are 10 samples in the diagram. Also, it is showing in this case, just to show this thing. So this is a two-dimensional. For example, consider this is a two-dimensional feature. There are 10 such features, and each are represented by the corresponding the value G1, G2, etc. So what it does, it finds that from the bottom itself. So at the bottommost layer, every element is a cluster, and then it incrementally builds those clusters. So the next will be it will build a cluster of 2, and it will go on adding every element to one of these clusters or creating a new cluster. So that is how it will go on doing it. So which means, for example, in this case, it assumes that G3 and G5 are the closest points, and they form a cluster. And so there is a set of G3, G5. So now instead of 10 clusters, you have 9 clusters, because one of these 2 has been now represented by a cluster. So again, you compute which are the closest 2 clusters. So here the distance between 2 clusters are defined. So I will come to that definition. So distance between points are easy to understand. Also, you can extend also distance between 2 sets of points, extend that concept. Very simple. There could be various definitions. One definition is consider all pair of distances between elements of 2 sets, and then you take the average. That is the distance between 2 sets. So there are different other definitions also. So at every step, we are finding out the 2 closest clusters and then merging them for the next hierarchy. So that is what we are going on. We are going on doing these things, and we are building the corresponding clusters, and also at different levels of hierarchies, the structures will be revealed. As you can see that with different colors, it is showing initially, the bottom level. Of course, all 10 things are there, but if you just go at certain level of hierarchy, this is called actually dendrogram. And if I take at any level, if I draw a line, for example, horizontal line, then it tells me that what are the groups. So this is one group, this is another group, this is another group, this is another group, this is another group. So it gives you the number of groups and it gives you that picture that no, what is the what kind of no clustering is there. So so this algorithm is very popular algorithm, particularly when you have high dimensional data also, and it is simple to implement. In fact, this example was given with respect to the bioinformatics applications where gene expression profiles are clustered, and those things are there. You can read many applications of clustering in bioinformatics because as I mentioned, unsupervised learning is a very powerful tool for scientific exploration. So just a rough description of this hierarchical clustering algorithm, which what I mentioned is simply those steps are described here. So you can see that your input is a distance matrix, n cross n distance matrix, and you are forming n clusters because there are n points, and then you form that hierarchical tree, which can be represented like a graph, but it's a tree actually. So for every vertex for each cluster, and if there is more than one cluster, so find the two closest clusters, C1 and C2, then merge them, and naturally merging means that you are including all their elements into a single cluster, and then you go on doing these things. So always you are finding two closest clusters, merging them till you reach at the root of the tree. That means all the elements are in the same clusters. So in this way you are adding a new vertex. These are the operations. When you are building up a tree, you need to do these operations. And if you are working with a matrix representation, so how are you manipulating with that matrix representations of this kind of tree or graph? So that is what is explained in that algorithm. And this is showing that how you can compute the distance between two clusters. So as I mentioned, there is no unique definition. There could be different definitions. It could be the minimum of all pairs of distances. It could be the average of all pairs of distances. So it could be other like Hadamard distance function, etc. that could be used. So I discussed about k-means clustering, and then we extended to the mixture of density function based grouping or clustering, and then we considered hierarchical clustering approach, and which gives you a tree and also graph-like of structure. But I will explicitly now discuss about another approach, which has a quite different flavor, and we call it graph-based approaches. Now there are here I will restrict to the analysis of I should say morphology of graph only, but there are different other approaches like spectral spectral decomposition based graph based approaches are there. So those are also very powerful approach for clustering. So I'm not going to discuss that. Using linear algebra concept, you have very nice theory and framework for doing that. But let me restrict to a simpler concepts of component-based analysis of graphs. Actually, cliques that we will be considering when you are trying to recover the clusters, retrieve the clusters. So the idea here is that once again, the representation of a graph from the input data set can be made from the distance matrix also. So because you are defining the similarities between say two feature vectors, and if you use distance and if you represent the distributions in terms of a graph, that means every feature vector forms a node of that graph, and you form an edge between two feature vectors if the distance is less than such a threshold. So it's a very simple naive representation, and sometimes this may not require to be explicit. It could be underlying representations. So whatever, if I give you this graph, then for the clustering, what is of our interest is that we would like to find cliques or connected components. So let me define these concepts like what is a clique? Now, a clique, of course, those who are from the computer science background, they already know it, that It is a graph with every vertex connected to every other vertex. Any query? Right. So examples are there. It is coming. So a click graph is a graph where each connected component is a click. So these are the examples of clicks, and also click graph could be an union of all these clicks. Any possible union? Is there anyone has any query? Sudipta, I think your microphone is unmuted. Right. So so this is what you have. There's an example of click graph. So the problem computation of clustering using graph is that suppose you have a graph, underlying graph representation. As I mentioned, that deriving a graph from your input data set could be also very trivial. It may be non-trivial also, because you may put certain constraints and then you try to derive that. But a very naive way of doing it is that define some distance function and use a threshold and define the edges between the nodes, where each node represents the corresponding feature vector. So in this way, you can get a graph. Now, the idea of clustering here is that you have to transform this graph to a click graph. So every click defines a cluster. So you can transform it. How you can transform? That means you have to either add some edges between vertices, or you can remove some edges between vertices. So the example what we give here, that you see that there are I think 7 vertices, and this is a graph. So if I remove these 2 edges, then you get a click graph. I hope that you have understood. If you remove these 2 edges, then you get a click graph, because all the components are clicks. But the problem is further is elaborated in the sense that there may be noise in your data sets. So the graph what you derive, some of the edges may not be the correct edges, but still the edges will be there, because this noise, you cannot eliminate completely this noise, and you assume there would be noise. Some of the edges are noisy. So that is how the question of corrupted click problems comes. That means just addition and removal may not be sufficient, or if you do it also, you can consider the smallest number, because there are various possibilities. Addition and removal, actually addition and removal requires because of this noise. If there is no noise, we assume that data are so strongly coupled and the clusters are so well defined that you get those clicks. That is the ideal situation. But because of that only, because of noise only, you are not really getting a click graph. You are getting which is not a click graph, but which should have some strong feature, which should lead to a click graph. I mean, there would be noise should not be too much. So that is a expectation. So the corrupted clicks problem says that what is the smallest number of additions, removals of edges that will transform a given input graph into a click graph. So this is the problem, and in fact we can show that this problem is also a NP-hard problem. And this is just elaboration. I mentioned already that how do you make get a graph from feature vectors. We can call it distance graph, because here you are using distances to define the edges. Use a distance threshold, and if the distance is less than that threshold, then you form an edge. And so that this is our expectation. So one of these examples, once again from this Pevsner's book, and in the domain of bioinformatics, you can see that it's a very good application. So that's why I just brought it into this slide. So here, let me explain a bit background. So matrix, this matrix shows you the gene expression profile. And you know that every gene is now represented by their expression profile. So this is the expression profiles, which are no, sorry, this is not expression profile. This is the distances. So gene expression profile matrix is not shown here. This is a distance matrix. This is a distance matter, I'm sorry. So gene expression profile would have been some no, expression profile, a feature vector of a very high dimensional or some d-dimensional feature vector, right? So when you compute the distance between them, then you get it is a distance matrix of the genes with their expression profile. So that's why all the diagonal elements, if you notice, it's a bit small in font. These are all zero, all the diagonal elements, and this is symmetric matrix. You are, I think so, this is symmetric. Yeah, this should be symmetric. Usually distance is symmetric. So this is a symmetric matrix. So in this way, you get a distance matrix. And now if you put a distance threshold 7, if you value, so you get, this is the kind of, no, this is the kind of distance graph. So this is one kind of problem in your, say, in your scientific study, you may get this kind of distance graph, and possibly this is the transformation can make it a possible, click graphs. And there, then you can find out the related genes which have similar expression profiles. You can put them into the same groups and you can study them. Motivation of unsupervised learning, as I mentioned, it is just the first step of initiating your scientific study. So this problem, the corrupted click problem, we'll be discussing further. And there are two techniques. As I mentioned, this problem is an NP-herd problem. And I will be considering two methods here. One is called parallel classification with codes, and another one is called cluster affinity search technique. So these two are quite popular, and this is discussed there also. So in the parallel classification with codes, in this technique, what it considers, actually in bioinformatics, we have a large number of data points, very large number, and also sometimes it could be also very high dimensional data, because you have good number of genes, and then you are trying to relate them, etc. Also, there could be various other kinds of data. Now, instead of performing clustering at a go for the whole data set, here the approach is that why don't you take a sample of it and do clustering there, and then you extend that clustering to the whole data set. That means you are trying to get a representation of that clusters. So that is what we call its extension. So this is what we have mentioned here. So suppose S prime is a subset of S, and you have performed a clustering on S prime, say K clustering. So it could be K-means clustering also, it could be. That's not an issue. Any clustering you can do. And then how do you extend the clustering to S? So it is quite simple. If I consider the K-means clustering, you have all centroids, and you can simply find out what is the closest one, and you extend it, right? But no, from the graph-based points of view, what we'll do, we will not go for that kind of center-based approach. Rather, we'll find out, given any particular element, how many edges are there to each cluster given that distance threshold, right? So if this number of edges is more, so this element is more prone to that kind of cluster, but it has to be normalized by the cluster size also, because if you have more number of elements in a cluster, the probability of having edges is also higher. So that is why we define a measure which is called cluster affinity measure, NJCI. As you can see, Ci is the cluster, J is the element, and this affinity measure, it says that it is the number of edges from J to Ci, that is NJCI, and affinity measure is normalized by the size of that particular cluster. And you assign J to that cluster which has the maximum affinity. So we are just modifying the concept of K-means here in terms of affinity measure. It's a definition with respect to your graphical representation. So the algorithm for this PCC is that you are taking a small sample. In fact, there are two stages of extension. Like you start with a very small sample, perform clustering there, extend with another set, which is bit larger set, of course, non-overlapping set, and then you get another cluster, again you extend with a very larger set. So you are doing it multi-stages because you are trying to make it more robust. So outliers, etc., effect are less. So there are analysis for that. So let us not go into that. We are just simply describing this process. So what we are doing, as I mentioned, it's a two stages extension. Randomly select S prime, a subset of S. Again, S double prime is subset from S minus S prime. So what you are doing, uh, you are considering, say, S prime is a log of n, and S prime is log n. So S prime, as I said, it has to be exclusive from S. So let me use pen to denote. So this subset, right, S double prime should be disjoint with respect to S prime. Also, it should be disjoint with respect to remaining part. So you have S prime, S double prime, and then the remaining part. So these are the things. So you are performing clustering, first level of clustering in S prime, then you are extending it, and then this is the second level of clusters. Then again you are extending it. That is what you are doing it. And this clustering is very naive in this concept. What it means, you randomly take all possible partitions. So it is such a small number, you can consider all possible partitions. So the number is given, k is given. So if I give you k, it is the size of S prime, that every element should have that many options. So it should be k to the power size of S prime. That many number of partitions are there. So if this number is manageable, that's why this number with respect to input data set is log of n. It's very small number with respect to the n. That exponentially it is decreasing this fraction. So you can consider having all possible partitions. For each partition, you form a cluster in the two stages extension. So that will give you a graph, right? Now, if I get a graph, then you count. Simply you count how many edges. So that is the graph, and this partition and this part. And this partition will give you the corresponding clustering. So find out that how many edges are to be removed or deleted to get this partition. So that would give you the score. So let me explain further with respect to this. So as I mentioned, you consider all k partitions and you perform these extensions and you choose the one which has the minimum score, that is number of edges required to add or remove from the G. I have an example here. So that the last stage particularly, suppose you have arrived at this particular graphical representation, and then suppose your partition was, say, 156 and 2374. That was the initial partition, that is the S prime's partition. And this is a full graph you get after two stages of extension. So now to how many edges are to be deleted or removed to get this partition? That means this is your click graph. So now you can see what are the extra edges are there and what are the edges which are not there. So if I enumerate them, you can find that edges to be added are this and edges to be deleted in G are this. So your score would be 10 if you count them. So you consider this process for every possible partitions with that small set S prime given K. And you finally choose those clusters, that partition, that means that is the cluster also after extensions, that will have the minimum score. So time complexity of this algorithm is quite simple to compute. As I mentioned, that for number of partitions will be this of the order of log n to the power log k, and each iterations you have order n square operations for extensions. So finally, total time complexity is this one for PCC. The other algorithm, which is called cluster affinity search technique, here also we are using the similar distance graphs, but here the approach is different. Here it is rather sequential kind of. So earlier we said parallel because you see that all the partitions are considered together, and then you are computing the scores. But here you are using a region drawing kind of concept. That means you are you are taking the clusters one by one. So you start from a seed point, start from a seed feature vectors, and then grow clusters which are near it. And then once there is a policy by which it will grow, and at certain point it has to stop, and then you take it out, and then you go on doing these things. So this is the idea. That is what you are considering here. Also, this affinity measure is used while adding any particular element to a cluster which is being under consideration, which is basically being constructed. So what we consider that for given any cluster, you compute the average distance between I and C, and the policy of inclusion of any feature vector to that cluster is that if this average distance is less than threshold theta, then it is close to that cluster. Otherwise, it is distant. So when I define a small cluster in the beginning, it may be a primitive single element. Then there will be iteratively you can always add the closest. I have said gene here because this algorithm was explained with respect to this gene representation, but it is basically a feature vector. So the closest feature vector, and then you are also removing the furthest feature vector. You go on doing this thing till there is no addition and removal. I mean, which satisfies all these conditions of, let's say, closeness. So this is the algorithms that you are simply going as I mentioned. You start with any point. Usually, you start with the vertex with having the maximal degree, and then you grow a cluster with this definition. That means you add the closest feature and you remove the furthest feature. So there would be this, and there will be a balance when actually your cluster has been grown in such a way that all the elements with respect to that definition, they are all closest. So there is nothing to remove, nothing to add. So when you reach that situation, so it looks convergence is an issue, but actually it is not. Practically, it has been found that convergence does not is very good, well maintained, and though it is not guaranteed, but it is in practice it is found it is fine. The last algorithm, which is also a very popular algorithm that I will discuss with respect to this graphical based approaches, and in fact, this algorithm does not talk about graph, but there is an implicit graph representation. We'll see with its definition. So it is called density-based spatial clustering of applications with noise. So it considers density of points and tries to group those points which are dense, which are dense in a particular space. So as I mentioned, it does not require any explicit computation of distance graph. So the idea here is that if you have a feature vector, then you can define a neighborhood around that feature vector in this way that there is a distance threshold epsilon. And if I assume this is an Euclidean distance, it would be hyperspherical in that space. So schematically, it is shown like that. So within that neighborhood, you count that how many feature points are there. So if this number is sufficient, then we declare this point is a core point, and all those points are neighbor to these core points, right? So those points also could be core points also, but a single point is a core point which satisfies this property that within its epsilon neighborhood, how many if the number of point is greater than certain threshold, then we call that point as core point. So these are certain concepts like core points. It is the number of point within epsilon more than a threshold k. So other threshold is k here, and these are called neighbors. And you grow regions of connected core points from a seed. So once again, it's like you can see that it has the flavor of cast algorithm. So it is also region growing algorithm, and you grow regions and then you delete region and you start doing it. So a neighbor, but not a core point, called a border point. So it will stop at those border points, because border points are not connected to, I mean, border points are not going to be expanded. Only core points are to be expanded. So you start with a point, and then you find out whether it is core or not. If it is core, then you go to its neighbor points. Again, you find out whether they are core or not. If there is a core, you expand and you go on doing these things. And if there are border points, you stop there. Sorry. So in this way, you are growing a region, and once you have grown a region, so you just take them out and again start this operation. And naturally, the seed point, initial seed point is taking an initial seed point will matter. So we try to get that seed point to get a good guess of that point where there is a good amount of densities there. So those are certain issues. Those implementations I'm not discussing. This is the principle, but I mention here, based on which this algorithm is defined. There is nice theoretical analysis, etc. You need to go through the papers and check it. So the advantage is that all this, and in these algorithms, so you see that this algorithm works directly in the feature space also. So it forms clusters of arbitrary shape. That is the advantage. In K-means clustering, I mentioned that major disadvantage was that it assumes kind of spherical distribution. And but it is computationally intensive. So because this distance computation, searching, etc., it's quite intensive. So you can use some kind of special index tree like R tree to make this neighborhood search efficient. So here we come to the end of this topic of this unsupervised learning. As I mentioned, under this topic, we basically discussed different kinds of clustering techniques. We considered semi-parametric approaches like K-means algorithm. That's a semi-parametric without explicitly mentioning any parametric estimation. But it is semi-parametric in the sense even you can also consider a kind of a parametric estimation. And then expectation maximization approach based where the mixture of Gaussians are computed, it is parametric in that case. Then hierarchical clustering methods we discussed. Then it builds a tree hierarchy following a bottom-up approach, and it uses distance matrix instead of explicit feature representation. That is what the characteristics of hierarchical clustering method, that what we discussed here, of course. And then finally, we discussed about some of these graph-based approaches, we have considered the computation of click graph. That means particularly the problem has been mapped to a corrupted click problem from distance graphs that can be derived from the feature space itself. So we need to solve this corrupted click problem, the problem statement I explained, and which means that you have to compute this number of additions and removals of edges, compute that transformation which has this feature, and then you get that graph which would be equivalent to a click graph. And then there are algorithms like PCC and CAST that we discussed. And finally, we also discussed another very popular algorithm, which is called DB-scan, which does not require any explicit computation of distance graph. But the concepts of this neighborhood and connectivity, those are also used there, as you can see. Distances, those are used. So with this, let me stop here.